Hello, my name is Ngọc Thanh Mai Trần. I'm from Politecnico di Torino and Istituto Nazionale di Ricerca Metrologica in Rome of Italy. For the moment, I'm doing the research period abroad for my PhD thesis in Korea Research Institute of Standards and Science, Greece, in Korea, under the supervision of Tanbi Kim and Won-Seok Kim. I'm going to present the calibration of 10 nanofarad capacitance from DC quantum Hall resistance using a digital impedance bridge. First, this slide shows the current traceability capacitance change from the DC quantum Hall resistance maintained at risk. The DC quantum Hall resistance standard was used to calibrate the 12.9 kilo-ohm AC to DC calculable resistor standard using the CCC bridge. This resistor has a calculable frequency performance, so it is then used to calibrate the two AC resistor standard of 103 kilo-ohm using an 8:1 ratio bridge. These two resistors are then employed to realize the capacitance of 1 nanofarad using a coaxial bridge. So as you see before, the traceability chain from a DC quantum Hall resistance requires an artifact of AC to DC calculable resistance standard. This is challenging to fabricate and has a lifespan based on a drift rate and instrumental errors like temperature coefficients. Hence, to replace the artifact of the resistance standards, further studies are being done for the AC quantum Hall resistance based on the graphene devices as suggested in the new traceability chain. In this work, for ultimate goal of tracing the capacitance from the AC quantum Hall resistance, preliminary study have been done for evaluation and calibration of 10 nanofarad capacitance standard using a multi-purpose and fully automated digital bridge. Here, in the new traceability chain, you can see that the primary standard of the DC quantum Hall resistance is used to calibrate the AC to DC calculable 1 kilo resistance using a CCC bridge. Based on the DC resistance value of 1 kilo resistor, that has a calculable frequency performance. The AC resistance value of 10 kilo resistor standard is calibrated using the 10:1 ratio bridge at 1.541 kHz. Then the 10 nanofarad capacitor can be calibrated from the 10 kilo AC standard resistor using a 10:1 ratio bridge at 1.541 kHz. At this frequency, the resistance to capacitance ratio is approximately 1:1. The 10 nanofarad capacitance can be measured against the 1 nanofarad capacitance from the current chain that presented before. So the two chains can be compared. I'm going to talk about the standards employed in the traceability chain that are the following. First, the 1 kilo AC to DC calculable resistance standard. The resistor is a Haddad-type resistor fabricated at Lenini. The evaluation of the 1 kilo AC to DC calculable standard resistor has been done for more than 2 years in terms of its stability and temperature dependence. The standard is placed in the temperature control chamber for a better stability. Its value is calibrated frequently by the direct current comparator, the DCC, and the CCC bridge. The results here in the top left picture shows a daily drift of about 3 times to 10 to the minus 9 per day. It's also noticed that here in the graph on the bottom right, the resistance value has a current dependence. The 10 kilo ohm AC standard resistor. The resistor is the VC resistor, model 516-4. The resistor is kept in a temperature-controlled enclosure, and its AC value has been calibrated regularly for a long time. In the right picture here, the red circle in the gray shade region are the calibration values obtained from an NPL. The black circle here, the last one, is the calibration value obtained from new chain. The value is stable within the daily drift of about 2 times 10 to the minus 9 per day. The 10 nanofarad standard capacitance. The 10 nanofarad is a commercial capacitor, model IS 1404 10 nanofarad. The capacitance value is observed to have some changes under the ambient environment due to the large temperature coefficient of the capacitance. Therefore, it is placed in a temperature-controlled chamber, and in the short term, stability has been improved, as you can see in the left figure. The capacitance ratio was measured between 10 nanofarad and 1 nanofarad using the 10:1 ratio bridge at two frequencies of 1 and 1.541 kHz. The figure in the top right shows the drift in the ratio. The drift is observed to be around 17 times 10 to the minus 9 per day of the measure value, and is believed to be the drift of the 10 nanofarad capacitance, since the drift of the 1 nanofarad capacitance is known to be 2 orders smaller. The capacitance ratio was measured against the varying voltage, and it seemed to be constant within the range of 0.5 times 10 to the minus 6. Fully digital bridge. The digital bridge employed in the experiment is developed by the Czech Metrology Institute, the CMI, and it can be reconfigurable in either digital assisted or fully digital mode. The bridge has been mainly evaluated in the digital assisted mode in the previous studies, so in this work we will focus on the fully digital mode. The schematic of the fully digital bridge is shown in the figure. The bridge is energized by a polyphase sine wave generator with two output channels. The sine wave generator are synchronized with a 10 MHz reference. The sine wave generator of G1A supplies the reference voltage to the null detector of a lock-in amplifier, model signal recovery 7280. G to A and B apply the voltages to the impedance standards of ZA and B as the main voltage sources. G3B, A and B inject the voltages for the high potential arm balance through Z high current A and B. G4B injects a voltage for the low potential arm balance. The injection voltages are applied through the injection transformer 1, 2, and 3 so that the bridge can fulfill the 4-terminal pair definition for the impedance measurements. In order to switch the measure point during the balancing procedure, a coaxial multiplexer is embedded. The bridge can be controlled remotely via the LabVIEW software. The automated process enables the impedance ratio measurement by one click within a few minutes. Under the fully digital mode, the impedance ratio of ZA and ZB can be defined by the ratio of the supply voltages of UA and UB as the below equations. ZA over ZB equal UA over UB, where UA and B corresponds to the voltages applied to G, A, and B. To improve the measurement uncertainty, the fully digital bridge measurement was done by taking an average between the two measurements of forward and reverse connections of the impedance standards. This helps to exclude most of the bridge systematic errors. This slide presents the resistance to resistance ratio measurement using the fully digital bridge. The 10:1 resistance ratio was measured using the fully digital bridge and compared with the reference value measured by the digital assisted bridge. The deviation in the graph was minimum at 2.5 volt with some parts in the order of 10 to the minus 6. The applied voltage could not be increased further due to the current limit of the 1 kilo ohm resistance standard. Next, the 10:1 capacitance ratio was measured using the fully digital bridge and compared with the reference value measured by the digital assisted bridge. First, the capacitance ratio of 100 picofarad to 10 picofarad was measured by varying the applied voltage at two frequencies of 1 and 1.541 kHz. The deviation of the measured ratio from the reference ratio is in the order of 10 to the minus 7 at 2.5 volt. The deviation was larger by 1 or 2 orders at the low voltage of 1 volt. The next figure in the top right shows the Allen deviation for the 100 picofarad to 10 picofarad comparison at 1 kilohertz at 5 volt. The residual voltage of the bridge after the balance reaches 2 nanovolt in about 200 seconds. The figure in the bottom left shows the capacitance ratio measurement results of 1 nanofarad to 100 picofarad and 10 nanofarad to 1 nanofarad ratio. The deviations seem to also have the minima near 2 volt, with the best results in the level of 10 to the minus 7. The 10:1 ratio measurement can have a larger measurement uncertainty compared with the 1:1 ratio due to the non-linearity of the voltage sources, which can also lead to the voltage dependence. Next is the 1:1 capacitance ratio was also measured by the fully digital bridge. We measure the 1 nanofarad to 1 nanofarad capacitance ratio against the applied voltages at two frequencies of 1 and 1.541 kHz. The results were then compared with those obtained from the digital assisted bridge. Here in the graph, shows the deviation lies within plus minus 1 times 10 to the minus 6 of the measure value, regardless of the applied voltages. Finally, here shows the comparison results between the 10 kilo ohm resistance and 10 nanofarad capacitance standards. The measure ratio of the resistance to the capacitance is in agreement of a few parts in 10 to the 6 at the best when compared to the reference ratio that was traced from the other chain. The Allen deviations shows that the residual voltage goes below 10 nanovolt after about 300 seconds at the applied voltage of 0.25 volt. The measurement result showed an unexpected voltage dependence. The resistance-capacitance ratio got differed for more than 10 to 10 to the minus 6 when applied voltage from 0.25 to 1 volt. From the previous measurement that's presented in the previous slides, the impedance standards themselves did not show any evidence about the voltage coefficients, and the 1-to-1 ratio measurement for the capacitance worked well for the fully digital bridge. So this voltage dependence will be studied further to find out the cause and effect. Summary. A fully automated and reconfigurable digital bridge has been employed for tracing the 10 nanofarad capacitance from the DC quantum Hall resistance. Studies for the bridge measurability evaluation have been done mainly in the fully digital mode, together with exploring the basic properties of the impedance standards, such as the 1 kilo ohm, the AC-DC calculable resistor, the 10 kilo ohm resistor, and the 10 nanofarad capacitor. The impedance standards were stable, and the fully digital bridge could measure the 1-to-1 or 10-to-1 capacitance to capacitance and resistance to resistance ratio with the accuracy of 10 to the minus 7 level at the best. The fully digital bridge was applied to measure the resistance to capacitance ratio measurement of 10 kilo ohm to 10 nanofarad. And the agreement with the reference value was a few parts in 10 to the 6 at the best, with some voltage dependencies, and it needs to be studied further. So thank you for your attention.